going. No sweat. Just want to get this going. We've got 45 minutes, and that's not a lot of time. So we'll get through as much as we can. All right, well, happy birthday. 1 day late. We have been social distancing since the big bang. So silly. Okay, so we're starting logarithms, which you have done in Algebra 2. So we don't treat it as though you've never ever seen it before. We're going to be graphing exponential and logarithmic functions. So logarithms are exponential expressions that are sort of inside out. So hiding under here, it says, well, this says, if you could not move that, that would be great. Okay, maybe I moved it. I don't know. I don't think I did though. All right, so it's a power to which a base is raised to produce a number, which typically for people doesn't mean a whole lot. But a logarithm is an exponent. That's the big deal. Logarithms are exponents. They follow rules of exponents. And what that means is, if you've got something written in logarithmic form, this is considered the base of the logarithm, and the answer is the exponent. Which is kind of weird. So if log base b of x equals y, that means that b to the power of y equals x. Sort of just inside out. It's actually the inverse. So this b and this b are just the base. I have no idea why it's doing this weird thing. It's like connecting lines. Little, I don't know. Anyway, okay, so this means b to the power of y is equal to x. That's what this is. Let's look at some of these that are back and forth. So in logarithmic form, log base 2 of 32 equals 5 means 2 to the power of 5 equals 32. Oh dear. Okay, so it means 2 to the 5th equals 32. Remember, or not remember, just notice that your answer is the exponent. So the answer to a logarithm is an exponent. Similarly, if I have this one, my base is 5, and this is saying 5 to the power of 0 equals 1. So under here are some more. I want you guys to do this, and then I'm going to call on people to write up what you think. So you've got these different ones. Just take a minute, and when you're ready, raise your hand. I'll wait for people to have a chance to do these, and then I'm going to assign you. And I will also assign somebody to check. So you'll have maybe more than one job as class progresses. Tyler. Fong. I'm so sorry, this writing is so tricky. Sarah. So if you would write your answer there. And then just put a check mark if you agree. This is Kristen. Caitlin. This is great. And Anish. So just put a check mark if it's correct. If it's not correct, put an X mark, and then we'll take a look at what's going on. Okay, cool. These are looking good. And they actually make sense, right? 10 to the first power is 10. 10 to the negative 1 is 0.1, or 1 over 10. And then 1/2 to the negative 1 flips 2 into the top. Okay, so let's go backwards and see what's happening the other direction. So 1 log base 2 of 16 equals 4. But the way that you say it is log base 2. Some people just go log 2 16, and that's not correct because it doesn't tell you really what's happening. Log base 2 of 16 equals 4. So, and the big deal with this is that 4 is your answer, and 4 is an exponent. So this is the same as this. Okay, so I'm going to do the same thing. Raise your hand as soon as you're done. So you want to convert these back into log form, and I will have somebody write it and somebody check it. Okay, good. All right, so here's people to actually do it. Nikki, Austin, Peter, David, Jess, and then people that are checking. Those guys. Oh, sorry. You didn't see that. Checked. Let's see. Moving up. Peter. Amanda. Connor. And let's see. How about Rachel? Okay, and Jeff, you don't need to write it in words. That was just so that you know how to do it. You just want to write it like this. Write it mathematically. So we've got okay, so I've got Nikki, this is 3 to the 5th, 243, 4 squared is 16, 5 cubed is 125, 1 half to the negative 3 is positive 27. Notice, and this is actually, it's good that I said negative, because these numbers in here cannot be negative. You can't raise a positive number to a power and get a negative, right? So I can't do, let's see if I can, there are certain restrictions on this. I can't say log base 2 of negative 16, because you're asking somebody to say, okay, 2 to what power equals negative 16. Well, my base is positive. So there's never going to be a number that is negative in here. That is one of the restrictions. Another restriction is that, let me get the color. Okay. Another restriction is that this number is not negative, so it's positive, and it's not equal to 1. My question to you is, it's positive, so you saw that right here. Why could it not be equal to 1? Just think about that. Why is it not possible for the base for a logarithm to be 1? Think of log base 1 of 7, log base 1 of 9, log base 1 of 25. Why is it not possible? what you were going to say too, Lydia? Exactly. Marsha, Che, very nice. So these are functions. That means I don't have multiple answers. So 1 to any power is going to be just 1. It can't possibly give me 7. So 1 to any power can't possibly equal 9. So you must be positive. You must not equal 1. And this number is also positive. How about this? What if I had log base 2 of 0 equals 12? Or log base 8 of 0 equals, I don't know, negative 5. What do you think about that? Yes, no? Is that possible? Just a big yes or no is fine. Okay, excellent. So that's also not possible. So I am not allowed, and it's not that I'm not allowed, it's not like somebody made a rule. If these things mean what they say they mean, well then I cannot possibly have a 0. So now we have one other stipulation. So if I've got log base b of x equals y, b cannot equal 1, b cannot equal 0, so b has to be greater than 1. This x cannot equal 0.
So one correction that I want to make, b does not have to be simply greater than 1. B could be anything between 0 and 1. So you could have a 1/2 power here, because you can raise 1/2 to some power and get a valid number. So this being greater than 1, it has to be greater than 0, so it can't be equal to 0, and it cannot be equal to 1. It doesn't actually have to be greater than 1. It can be a fraction as long as that fraction is not 0, like 0 over something, or as long as it doesn't result in 1. Just wanted to clarify that.
Okay, let's move it on. Okay, how many of you have heard of the number E? Just want you to raise your hand. Never heard of it? That's totally fine. Just raise your hand if you've heard of E. Wow. I'm blown away. I am blown away. Jane, what do you know about E? You've heard of it. Do you remember what it is or what the heck is going on with it? Fine if you don't.
I know E is equal to 2.7.
Okay, good. It's really close to 2.7. E is approximately 2.71828, blah, blah, blah. It goes on and on and on. And it's important because it comes up, it's called the natural base. And this thing comes up in natural situations all the time. Why? We don't really know. But things will grow exponentially according to the base E. Natural things. Trees and, I shouldn't say trees, but certain fractals, which actually is related to trees. But there are certain things like bacterial growth, exponential decay. Most of them in nature have a base of E, which is really strange. What other kinds of irrational numbers do you know? Give me another example of an, okay, good, pi. Pi is one of them. Anything else you can think of? Definitely pi. Beautiful. So pi, square roots of weird numbers like 2, cube roots of, oh wait, actually no, that would work too. Like the cube root of 5. That's irrational. I don't know what that is. So by irrational, that means I cannot write it as the ratio of two numbers. We even try. I think the Chinese said pi is approximately equal to 22 over 7, but that's really not. Pi is the relationship between the circumference of a circle and its diameter. And people have tried to come up with it. This is the age-old question. Well, here is calculus. We will do this. The limit of blah, blah, blah. So if you were to put this into your calculator, y equals this, 1 plus 1 over x to the x, and then you go to your table, or you let it pop out values forever and ever and ever, this will be as close as you want to 2.71828. I don't know what the rest of it is. That's about the most I know. It's the sum of this series, which is fantastic. You have no idea why, and that's fine. And hiding under here, I thought was something exciting. I'm pretty sure there's something exciting. Okay. So, and this is what I was talking about before. This is a natural base. If I say log base e of x, another way to write it, because mathematicians are really quite lazy, is ln. That comes from Latin. So if you're a Latin person, you now know yet another Latin idea. ln, the L is logarithm. The N is natural. So if you see ln 5, your calculator is telling you e to some power equals 5. And it's only approximately equal. It can't really be equal because e itself is an irrational number. Okay. On your calculator, it's kind of weird. They write L, and they put it in capital letters. Nobody does that except for your calculator. Calculator is special. Okay. Let's go back and forth. With no calculator, we can do these. And the way that you can do them is kind of sneaky smart. Let me get rid of some of this stuff. Okay. So I'm going to set this equal to x. And then I'm going to say, all right, 2 to some power equals 32. Now, when it's not really easy like this, some of you will probably know, oh, that's 2 to the blah, blah. You can rewrite it. You can say, well, this is 2 to the power of x equals 2 to the 5th. And then if your bases are the same, 2 to the x and 2 to the 5th are the same, well, clearly your exponents also have to be the same. So then x has to equal 5. Okay? Some of you can just talk about the answer. That's completely fine, too. But there are some times that it's easier. Whoa. I didn't mean to do that. X is equal to 5. Right? So if I use that principle for the next one, call that x, I'm going to say 4 to some power is equal to 2. What you're trying to do is write the bases the same. So this 2 and that 2, or 4 needs to be written as a 2. So if I say 2 squared to the x equals 2, remember that's just 2 to the first. So analytically, you would say 2 to the 2x equals 2 to the first. Equate your exponents, and you get 2x equals 1, or x equals 1/2. Kind of strange. But if you think about it, if I've got 4 to some power equals 2, think about 4 to the 1/2. What does 4 to the 1/2 mean? How else could I write that? Caitlin, how else could I write 4 to the 1/2?
You want me to write it? Or?
No, you can just say it. You can just say it. I don't need you to write it. How would you write that?
4 to the 1/2, that is what? 4 to the 1/2, that is what?
Be careful. 1/2 powers, 1/3 powers. Let's see.
So that's negative. That's not bad.
around about that in calculus because there was a problem that needed that property, and people were making the same error. So that's a good error to make. How else, though, could I rewrite this? 4 to the 1/2 is the same as what?
2, because it's square root.
Right, it's going to be 2. But what does the 1/2 power mean? If I wrote that without the power. Say it again.
Square root.
Beautiful. So square root of 4 is equal to 2, which we all agree on. Right? Take a look at this one. I'll set this guy equal to x. That means 3 to some power is equal to 1. Shout it out. This one I can't even write with the same base. Not even possible. I guess I could. Yeah. I guess I could, and I could say 3 to the x is even. Equal to 3 to the 0, but nobody does that. This is one where you wouldn't rewrite it as the same base. Here, x is just 0. Nice. Okay. 0, done. Okay. Well, all right. Let me take a look at what's going on under here. Hiding. Okay. All right. So let me get rid of. Actually, let me lock the background. Otherwise. And what I want you guys, actually, let me do one more, and then I'm going to start assigning these. Here. Get rid of this and that. Move some things. All right, let's try this. Okay. So take a look at this first one. This is saying, so I'm talking about example 20. So don't worry about that weirdo 7th root. So that's the 7th root. You would say, all right, the 7th root of 4. How did I write 0? That was stupid. I meant to write x. Okay, so this is saying 7th root of 4 raised to some power equals 64. So make sure that this makes sense first. I'm going to make sure it makes sense. Here's my base. My exponent is what I'm looking for. And I need that base to this exponent to equal 64. So I'm going to rewrite this, the 7th root of 4 to the x, using what we talked about, what Caitlin was giving me when we did the -1/2. So if I rewrite this, I've got 4 to the x over 7 equals 64. Okay. All right. I need to write these using the same base. I need 4 and 64 to have the same base. So you look at the bigger one, typically. What base could I rewrite 64 as to get 4? You can just shout this out. I don't need you to wait. X. Very nice. So 4 cubed is 64. So I could say 4 to the x over 7 equals 4 to the 3rd. Now you could have used a base of 2 also. You would just have 2 to the 6th. That's fine too. But then once you have this, the beautiful thing is you can solve this. So x over 7 is 3. And x equals 21. Okay? So I want you to do the same thing. Some of them are going to be just visual ones. Other ones, you're going to want to rewrite it with an x. So I'm going to give you just a few minutes, and then I shall assign a person to do it and a person to check. Give me a gigantic line. Okay, let's try this again. Is my base, that 3 and this 3, match? Notice that your answer is 2. So what's kind of cool is if you see a base that matches the argument, is what we call this. You got a 3 and a 3 and you got a 2. So that also means had I don't know, log base 7 of 7 to the 12th, your answer would be 12. So if this base matches the argument, and the one that's hiding under here was the same idea. It was something like, get a different color. It was something like 2 to the log base 3 of 5. I'm just kidding. 3 to the log base 3 of 5. That is just 5. So if the base matches the other base, your answer is just the exponent. So if I have, I don't know, 12 to the log base 12 of x squared, that's just x squared. Those are properties that we'll get to a little bit later, but I just wanted to show you that what I had covered up was not a big deal. Okay, we're going to get into graphing. So if you don't have your calculator, grab your calculator, and I'm going to wait. I want you guys to put a little check mark next to your name if you have a calculator. Okay, we'll do this. Actually, no, I'll just remove these things. These are going to be related to each other. Okay, so on this first one, I want you to graph y equals 3 to the x. On this one, I want you to graph y equals log base 3 of x. Now, there's a little button that allows you to do a log base. So I'll put the keystrokes for that in just a second. But in the meantime, go ahead and graph those. Sketch an itty-bitty graph for yourself. Look at the characteristics of it. And I'll give you about a minute to do those, and while I'm at it, I will write up the keystrokes for this. Okay, so to get that log base 3 for this one, go to alpha, you hit window, which is F2, and then choose number 5, and it will allow you to put this log base whatever in your life. How did you do it?
I hit the math button and it's to laugh.
Yes. That's another way you can do it. There are several different ways. You could even do alpha y equals and scroll over. So however you want to do it is fine. Sometimes people forget about the math button, or they do it and then they just don't see it. So another way you can do it if you want to is math, and then choose the last one. It's just that you don't see it, so sometimes you forget. Those are the ones I actually want you to graph. And then I'll write in a different color the people who are going to check. So, Connor, did you get values for 0, blah, and 1, blah? Did you get values for those? Oh, nice. Yeah, you must have. Otherwise, you couldn't have graphed it. So notice a couple of things. First of all, you have a gigantic asymptote. right? These are not going to go below 0 if you are an exponential and you're not messed around with. And I'll tell you what that means in just a second. So y equals 0 is going to be your, what is it called? Asymptote. It's a horizontal asymptote. Notice logs are just inside out exponential functions. They are the inverses. So it is not a big surprise that what used to be a y equals asymptote is now an x equals asymptote. And these are key points. So at 0, this is going through at 1. At 1, this is going through at 3, which is really hard to draw on here. Similarly with this, 0, 1, there's 0, 1. 1, 5, wow, it's so hard to draw that. Well, this works the same way, so I could reverse these. 1, 0. So really, you could draw the exponential function if you want to, and then just reverse the points. So this becomes 1, 0. This becomes 5, 1 on this graph. So get a different color. So that I'm talking about this point and 1, 5, which is beautiful. Tyler, you did a great job there. I'm glad that you agreed. Similarly with this one. So this will be 1, 0, and 3, 1. So those are guides to help you. And so now we can do this. We can put it all together. If I have b to the x, 0, 1, and 1, b. So I don't know where the b is because I don't know what it is. But I've got this curve. Without messing around with it, it has a natural asymptote at 0, meaning y equals 0. And then it's inverse. So if I switch x and y, just so that you see what's going on. If I switch x and y, and I say x equals b, oh, shoot, you don't know that yet. Okay, never mind. I would have done something, but it requires that you know something else. That's fine. Okay, so similar thing with this one. This is going to be B0. And then, let me write these points here too. 0, 1, 1, B. And this is 1, 0. Get rid of this. I gotta move my B. Okay, let me grab this guy and move it. Sometimes it's easier to write it exponentially and then flip your points. That's up to you. Okay, so 0, 1, and then becomes 1, 0, and then this becomes B1. So wherever B is, you go up 1. There's my B. And then my asymptote is the y-axis. Okay, domain and range, just reverse also. So my domain for this is all real numbers. My range is what? So Ryan, what is my range for this? My domain is everything. What about my range?
0 to 0.
Nice. What about 0? Is it included or no?
No.
Good. All right. And notice these are, you can look at the graph. Here my domain is 0 to infinity, and my range is negative infinity to infinity, which is not a big surprise because whatever my range is for the 1, the range in the domain, and I'm going to get rid of this because it's confusing to me to see the PR. Okay. So whatever the range is for 1, that becomes the domain. So they reverse because they're inverses. Not a big surprise. All right, so I want to give you some practice with these being moved. We're going to move them all over the place. I'll be shifting them up and down and putting negatives in for x's. It looks like, Nikki, did you have a question? Your little text box you didn't put up. Okay. All right. Take a look at this. the x plus 2, what do you imagine the plus 2 will do to it? What will happen with the plus 2? Move it up, down, left, right. Beautiful. Vertical shift, translated. I love the math notation for this. So you can either graph the original one and then shift it, or you can just shift it immediately. A lot of times I'll graph the original one, just like with a little x. So this is, if I had graphed the parent function, y equals 3 to the x, it would have been 0, 1, 1, 3. But I'm shifting everybody up. So let me shift. 1, 2, 3. This guy is now here. And I'm going to go right off. Like, oh, shoot, I'm going up 2. Sorry. 2. So however you want to do this is completely fine. When you've got things shifting up and it's exponential, that means your, what is this called? Your asymptote also shifts. So everybody goes up 2. So now you have different key points. You've got 0, 3, and 1, 5. So those would be key points. So if something asks you for key points, that's what we're talking about. And I just want to talk through the other ones because you can see all of the rules that you had for quadratics and for everything else that you've done, that applies. If I've got a 2 hanging out on the outside, it's going to shift it up and down. If I have a 2 in front, you'll have a vertical stretch. If I have a 2 with the x, we'll shift it left or right. And the same thing happens with logs. So if I'm graphing that, I can do the same thing. So I know that these are inverse functions. I could graph log base 3 of x and then shift that also. So log base 3 of x, which would give you 1, 0, and 3, 1. So it would have been there, but I'm not going to do that because I'm shifting it up 2. So same thing applies. And I'll do this in a different log. So if I shift this up to here, if I shift this guy up to here, my asymptote you don't see. So you're not going to see your asymptote moving anywhere because it's a vertical line. So if I shift it up, it just does the same thing. The only time that would happen is if I were shifting it left and right. Okay, so once you hit the basic graphs, I'm just going to uncover these ones and ask you some questions about them. Smiley face, funky face, approving, thumbs up. If you have thumbs down, it's totally fine too. I don't mind. Okay, so I'm just going to talk through the rest of these because I know you guys are smarter than smart. I'm so happy you're here. I miss seeing your pretty faces. Your smiley faces. So this guy, x plus 4, is going to move it what? Left or right? Just shout it out. Left or right 4? Left. Very nice. And then same thing happens with this guy. So your asymptote's going to move. Let me advertise the next one. What does this negative out front do? Does it flip it over the x or over the y? So you don't just want to say reflects, although you're right, good. So it's going to flip it over the x-axis. And similarly with, so we were going to do all of these, but I don't want to take the time. Negative outside, so that's going to reflect over the x-axis, just like before. If I have a negative with the x, that flips it over y, and don't worry about the negative in here. Remember we said you can't have negative numbers in here? Well, that's true, but if x is a negative, that makes this positive. So it's going to be in this quadrant instead of over here. Don't panic. I think that's it. These 2's on the outside, those are going to stretch, just like you would imagine. If I had a 5, it would stretch it vertically. It would change that. E to the x, the only difference is your base is this weirdo e. It's 2.71828. Similarly with this. So these are also inverses of each other. You don't see that. And then these are the same things. If your base is weird, e to the x is one thing, ln is the flip. If you got a -4, it's going to shift down 4. So these are not any different. It's just your base is a weird irrational number. And the ln, remember, means log base e. It used to really bother me to see ln. So I would write, just wrote ln. I would write log base e of x, because it just bugged me. This ln just looked weird. So I always rewrote it until I got used to it, and then I stopped doing that. Okay. So I'm imagining that you guys are okay. I do have an exit ticket, a fun exit ticket, which is just sort of a recap-ish thing. How are you doing? Are you having